All right, so as we get going here, let's kind of do a little bit of a recap of what we talked about when we were together last week, and then we will jump into a little bit more in the way of details. We started talking about this idea of a new changing architecture that's available for enterprise data storage, and that is this idea of an in-memory column store database. And one example of that, in fact, what SAP claims to have pioneered, although they actually bought the product from Sybase and then or bought the patents from Sybase and then developed some products related to it, is this idea of a in-memory column store database, which they have brought to market under the name brand of SAP HANA. And we looked last time at this pictorial representation, which SAP uses, that highlights really the four key elements of the HANA architecture that we'll spend more time talking about most of these, if not all of them, in our time together today. And that is, we look at a fairly powerful piece of hardware, and that this is going to be a server that has as many CPUs as we can reasonably throw at it, given the bounds of contemporary computing. We're going to look at doing away with hard drives and other slow data storage vehicles of that type and move to in-memory data storage. We're going to change the fundamental structure of the database in that we're going to look at being able to store data in a column store format, and this concept of an insert-only database. And we will talk about all of those things together today. At the end of our time, last time, a question came up, which I said, let's talk about that next time. And it was this idea of, if we're going to have an in-memory database, which, just to clarify here, we are talking about putting our entire database in RAM memory, which, if you know anything about even the basics of computer hardware, that's volatile memory, which means that if the power goes out, you lose that data. So what does that mean? And the answer is exactly that. If the power goes out, you lose that data. So how is that a reasonable solution? Well, the first thing to note is that in a contemporary data center, the power should never go out. That's actually not as common an experience as you might think. It's not unusual for data centers to, not have power outages in periods of time that could be measured in years. But let's assume, for the sake of argument, that the power does go out. Well, there are several different solutions to this. One of them is that your database could be in memory, but you have hard drives that are providing backup. The challenge with that is, and the way that architecture is actually affected is pretty straightforward. I mean, basically you just have a data fork, and as you're writing things to RAM, you're also writing a copy of it to a hard drive or flash memory or something of that sort. The reason why, though, even that is challenging is you're talking about a lot of data being written to a hard drive. So in actual real-world performance, when you're looking at restoring that database off of the hard drive, you could be looking at that taking days for that level of data recovery. That's no good. That means potentially you could be down and out of operation for days. So how do you solve that? Well, there's lots of different strategies, but one of the very popular ones for multinational companies in particular is they look at it in terms of, okay, we're going to put these machines in data centers. And so let's assume we're using Amazon as a part of this. So we might have something at a data center in Virginia, and then we might have something on the West Coast, so we would have something in California, and then we would have perhaps a data center in Europe somewhere, and perhaps a data center in Africa somewhere. Well, the idea is that all four of those locations would have the same data, because we would be peering data across all of those data centers. So the more typical solution is, if all of these are employing a HANA system and the Virginia system does suffer a power outage, then what you do is you just reroute your traffic to the three other systems, and then when it comes to bringing the Virginia data center data back up, you don't look to hard drives to do that. You just copy it over from one of the data centers that didn't lose power. So the idea here of having redundant data centers is the more typical approach here. And it kind of is a byproduct of the fact that putting these in different locations around the world makes good sense from a data handling perspective, and so you take advantage of that redundancy as opposed to spending a lot of time worrying about the power going out. And so this is the most common way that that's solved. But there's no magic here. It is true, if the machine does lose power, you do lose that data. Questions about that? Yes, sir.
Restoring from a remote location is faster than restoring from disk. Means that it's because saving to disk, and when you have to start again, you have to look up everything from disk. And what this approach you just suggested,
I don't think you said restore in that case. You said we're talking about routing. Right.
no, after the routing, the system that was down would have to come back up, and it has to be copied from a remote location to. So I'm saying copying over the import compared to copying from disk is the advantage of that compared to disk.
If I understood you right, it is actually, this is one of those things that's kind of ironic. You can actually restore across a network faster than you can pull it back from a hard drive with contemporary data centers. I mean, it's just kind of, this is a level of internet speed that you wouldn't have at your home. I mean, but they can move just massive amounts of data in a very short period of time. Yeah, so you're looking at it actually being faster to move it across a network than you are restoring it from a hard drive that's sitting in the machine. One of the problems is, and we'll talk about this a lot, hard drives are just slow. I mean, it's at this point, it's old technology that really only continues to be used because it's cheap and because we have a lot of devices that don't need the high performance. I have a DVR at home. In that DVR, there's a 1 terabyte hard drive. It's not a fast hard drive, but it's fast enough for video recording. But I think that probably in the next decade, you're going to see hard drives go away. You're already starting to see that in most laptops anymore. And I think you're just going to see them fade away as the other alternatives become a lot cheaper. So, you do have them available, and we may have time to talk about today. There is also with HANA the idea of what's called hot, warm, and cold storage. And hard drives can be very useful for cold storage, which is data that you have to keep, but you may actually never have to look at it unless you're audited or you find a need to go back in time and look at stuff. And so things that used to be put on tape or other things like that, a lot of times now are actually put on hard drives because it's so cheap. So any other questions about the in-memory, the volatility aspect of that? All right, so we will continue our discussion, and I want to back up one more slide here just by way of discussion. So how do we take a database and put it in memory? Could you just take a database that your company is running that's a traditional old school database, and could you put it in memory? Well, if your company is any size at all, the answer to that is probably no, because the database is going to be too large. You're going to need you would need a machine hypothetically with 12, 20, 24 or more terabytes of RAM. There's a point at which that becomes way too expensive to even consider. So how do we put a database in memory? And the answer to that is the four things that I have listed at the top of this slide, which is what we're getting ready to talk about. We're going to talk about this idea of row store versus column store databases. We're going to talk about the concept of dictionary encoding and show you how that works. We'll talk about attribute vectors, and then we'll talk a little bit about compression, although that aspect of this gets very, very complicated, and there's not a lot of need for us to dig into the nitty-gritty of that in order to understand the overall system. So the very first thing that we really need to understand is this idea of row store versus column store databases. And I'll just go ahead and tell you by way of getting started here, traditional databases are row store databases, okay? And so we're going to move here, and I'll send you, I'll upload into D2L all of these resources that I'm using here so that you'll have it along with the videos and such. This is a table that I created in Microsoft Excel. Created this a year and a half or so ago for the sake of a presentation on this topic, and this shows all of our U.S. presidents up to but not including our current presidents. So this would be an example of a database table. We have a last name field, we have a first name field, we have a state field, and we have a party field. And by the way, I got all of this data from that unimpeachable data source, Wikipedia, okay? So they're the ones who said what particular party someone is in, and you know, probably at some point in my life I memorized the US presidents, but I could no longer do that from memory, so I just created this from Wikipedia. So you can see, you know, although we're looking at this in Excel, it's very easy to understand this as being a database table with, in fact, 4 different fields, and there are 44 rows because, as I mentioned, our current president is not included. Well, what does it mean if we say a row store database? And this item that I have a picture of here in the upper right hand corner is something we don't see too much anymore in contemporary technology. Maybe some of you have seen before reel-to-reel tape decks, where you would use those kinds of reels in conjunction with a device for recording audio. If you can remember back to the days of VCRs, you had this kind of structure inside a VCR tape shell. Same thing with cassette tapes for audio. We showed a picture last time, let me pull it back up here, of the magnetic tape like you see in the background here of this picture of the IBM 360. Well, why am I showing you pictures of tape like this, and what does it have to do with row store and column store? I think that this will help you understand why the data is stored the way it is and what it means for us in terms of access. So how did these magnetic tapes actually work? Well, what's not shown in my picture is that kind of sitting right here in the middle was some kind of device that would serve as a read-write head. And so if you were actually writing data to this tape, what would happen is the tape would start turning very, very slowly, and then this particular write head in this instance would write onto the tape with magnetic bits the data, and then when it came time for you to retrieve the information, you would rewind the tape and you'd run it back through again, this time with that head serving as a read head. Well, this was the way that computers in the very early days stored information, was on this magnetic tape. Well, we now know that magnetic tape has gone away, and as we were talking about a moment ago, hard drives replaced them. Well, in actuality, the idea of data being written to a storage medium in linear fashion continued even in the era of hard drives. The only difference with a hard drive is you had concentric circles, and you had a read-write head that could move back and forth across these concentric circles as they rotated. But still, when you got right down to it, you're writing a bit stream in a linear mechanism. So when we say row store database, here's all that we mean. When the data is written to storage, we write it, if you will, scanning across the table from left to right, writing row by row by row. So if we were to look at what was written on this magnetic tape, what we would see is, and it's the same information that's on the table at the left, we'd write Washington, then George, then Virginia, then Independent, and we'd be at the end of that record. And so we'd go to the next record, and we'd write Adams, John, Massachusetts Federalist. And then we'd go to the next record, Jefferson, Thomas, Virginia Democrat, and we would just write out the entire table, traversing it row by row by row. It's a row store database. That's the way the vast majority of databases worked. That's the way relational databases worked from the beginning of their inception, and it's still the way row store databases work today. If you think about this from a computational perspective, the idea here is we are storing this information stored based on keeping records together. So the idea was this. If I asked you the question, what state and party was Abraham Lincoln from? And you had to play computer on that. And imagine you had the magnetic tape as your method of reading and writing. Well, what you would do, what the computer would do, would be scan through that magnetic tape very quickly, looking for Lincoln, looking for that word. And then when it found Lincoln, it would slow down the tape head and scan across that particular record. And all of the information about Lincoln would be stored in his record, which is all right there together. So, if we think about this method of storage, the big advantage of it is it's very easy to find a given record and retrieve that whole record. So let me ask you this. You are doing some database programming, and you're going to write a query, and you want to retrieve the entire record. What's the database command that's going to give you back an entire record? Well, select last name is going to give you back the last name. What's that? Select star. Yeah, this is optimized around select star. If I say select star where last name equals Tyler, this is optimized for that. We find Tyler and boom, the whole record is right there. Now in this case, the whole record only has 4 fields in it, but if it had 100 fields, once I find Tyler, all 100 of those fields are going to be there contiguous. So it will be very, very easy now for me to do a select star. Select star is computationally efficient. What is not computationally efficient is the con here is it is hard to retrieve individual attributes. So suppose we, for example, wanted to do a query that was something along the lines of select unique state. And then we had the rest of the query there. But the net effect was we just want to pull out all of the states and create a unique list of every state that has had a U.S. president from it, which clearly is not all 50 states. Tennessee is up there, but there's an awful lot of states not represented. Well, once again, put yourself in the shoes of this magnetic tape reel. What would you have to do? You'd have to scan through, find the first record, jump to the state field and read it. Then you'd have to jump to the second record, scan to the state field and read it. Then you'd have to jump to the third record, scan to the state field and read it. You're going to have to traverse an awful lot of tape and do an awful lot of speeding up and slowing down in order to retrieve that kind of information. So when the decision was made about how do we store this, there was a bias towards saying, let's put an entire record together. And so let's store it in this row-oriented format under the theory that we're going to probably be doing a lot more select star type operations than we are going to be jumping through the data. Now, we'll come back to this thought, but remember what we've talked about as being the difference between an OLTP database and an OLAP database, where one of them is primarily serving as a vacuum to store a lot of information, where the other one is more focused on getting data out. I trust you can see already that this structure is probably pretty good for OLTP, but it may be not ideal for an OLAP type query. So what's our option? The other option is column store database. Same database table, and here's the thing, a lot of people think, okay, we're talking about a column store database, that means everything changes. Well, no, it doesn't. The same picture is the same mental model of the database. The only thing that changes is when the data is stored, instead of traversing, if you will, left to right, field by field by field in a record, now we're going to write from top to bottom to a column and then move to the next column. So in this case, we would write Washington, Adams, Jefferson, Madison, Monroe, Adams, Jackson, Van Buren, Harrison. We'd write all the last names, and then when we got to the end, we'd come back up to the top and write all the first names. And then we'd write all the states, and then we'd write all the parties. This is the way a column store database table stores its information. So instead of storing this based on keeping records together, this is, let me get my pen to work again here. For some reason, there we go, stored. That's so funny. It'll like work as a pen over here, but not when I get over there. So stored based on keeping fields together. So in a row store, boy, that's horrible. I don't know why my pen wants to be a cursor over here, but over here it will write. One of these days I will figure out why Microsoft products work the way they do. And my pen, all right, so we'll just have to bear with it here. So the idea here is we're going to store the fields together. So the pro, now I'm back to being able to use my pen again. The pro is it's easy to retrieve attributes, right? My query a moment ago of produce a unique list of all the states, well, that just got a lot easier because I find the state field and then I can just scan through that list. It's all stored right there together. The con, what is very computationally expensive in a column store database?
I agree with I agree with queries.
Okay, or what would be a simpler way of saying that? What's the advantage of row store? What does row store make easy for us to do? Retrieving a record, right? What's hard to do in a column store? Reconstruct a record. Because now I've got to pull the last name out of that column, and then I've got to navigate to the first name, and then I've got to navigate to the state as to reconstruct a record is a lot harder. Now, that's the difference between row store and column store. And when I do this training a lot of times, I've done this for several companies, when I get to this point, everybody looks at me like, okay, that's not a big deal. Why does everybody make a big deal out of this? And what's magical about a column store database? Well, the magic is yet to come. But it's not that complicated when you get right down to it. Row store database, we write a row, and then another row, and then another row. Column store, we basically just turn everything 90 degrees, and we write a column by a column by a column by a column. So now the question is, what's so magical about this? What is it about column store databases that allows us to pick up computational efficiency? And the answer to that is what you see when you look at the data. And so let's look at some different pictures here. Suppose we're just going to focus on the party field. And all I have done here is I have color-coded the party, right? So you can see Independents picked up that like beige color, and Federalist picked up blue, and Democratic Republican picked up that kind of, I don't know what color that is, like a pinkish color. You can see the colors there. Now, if I were to say right now, pull out a piece of paper and write down all the parties, okay? And I asked you to do that. A lot of you would do something to make your job easier. If I asked you to write down that list of parties, what might you do to make it easier for your hand to actually do that, particularly if you wanted to do it quickly? Anybody have any ideas? Okay, you could write part of the word. That would be a good strategy. What else could you do? Notice what happens when we get to right here. And we have 4 of those guys in a row. And here we have another set of 4 of these guys in a row right here. Well, have you ever used those where you make the little, like, I think they're called Ditto Marks. It's like just a little double line, and that means the same thing over again. You know, you might write Independent, then Federalist, then Democratic Republican one time, and underneath that put Ditto Marks, then another set of Ditto Marks, then another set of Ditto Marks. Just indicate that Democratic Republican shows up 4 times. Then you might write out Democratic, and then you might put those Ditto Marks. Well, the point I'm making is when we turn the table 90 degrees and we start just placing our focus on an individual field, and we start thinking about ways that we could write out that data, there's some shortcuts that we could take that might work in our favor. Now, here I've done some color coding. Now I'm going to do some dictionary encoding. I've left the colors just to make it easier for us. But notice I've done 2 things now. I've created on the right something called a party dictionary, which I like because that sounds really, really fun, but it's really not, I suppose. And notice what I did in the party dictionary. I listed all of the party values, and I numbered them. In this case, of course, being a good computer scientist, I started at 0, and you see we have 6 different values represented there by numbers 0 through 5, and then I went over to the party field, and I did not write down the text. I put a number in there. Now, in doing it this way, we haven't lost any information. If I said to you, what party was James Madison in? You could find James Madison. He's on the 4th row. You see a 1 there for party. You cross-reference it with the party dictionary, and you say, oh, he was a Democratic Republican. Now, this may not look like a big deal, but computationally, this has just done something pretty magical for us. What has it done? Well, what it has done, I've saved a lot of space because the party only appears in full text one time. So I have every party is just spelled out in full text one time, and then every other place it appears, I've put a number there. Now, Democratic, let's think of it this way. If you were designing a database table, one of the things you always have to think about is how wide should a particular field be? You know, how much space do I need to leave? And if you look at this, if we assume that there aren't going to be any more parties appear in the future, and this is a reasonable list of parties, the longest name of a party up there is Democratic Republican. That's pretty huge. So the old way, we would have to create a field wide enough to store Democratic Republican, and every record would have a field that space in it, even though I might not need all of that space. Well, if I store it one time, and then I use those indexes, I can do something even more magical here, which is, if we think about this in terms of bits, right? Because computers operate on bits. I have 6 different values, the numbers 0 through 5. How many bits do I need to account for the numbers 0 through 5? Oh no, it's nowhere close to 24 bits. Let's look at it. The first bit would give me either 0 or 1, and then if I move out here, what's that in binary? That's what? That's 3, right? You're going to have to check me on this. It's been a while since I've done this. This right here is what? It's over 5, right? So I only need 3 bits. Now think about it. That means that entire party, instead of every one of those records having enough space to store the full word Democratic Republican, I'll need 3 bits. Every one of those records now only need 3 bits to store the party if I break it up into this idea of having a dictionary and having this right here. By the way, this guy over here, what's this called? It's a term I've already thrown out in a slide. This is an attribute vector. An attribute vector is a set of attributes. That's an alternate term for a field. And it's just a vector. It's just a continuous set of values that in this case are paired with a dictionary. So let's keep expanding on this. So what I have done here now is, you can see I've bit encoded it. Okay, I'll make this a little bit bigger so that we can all see, and then we'll look at a few different things here. So over here now you can see all the parties are just bit encoded. And over here is my bitwise party dictionary. All I did was convert our normal numbers base 10 to their bitwise equivalent. And so if we go down here to the bottom and look at this, and then we'll come back up to the top and talk of this, instead of values stored for each field being 21 characters long, because Democratic-Republican is 21 characters long. So the old way we would have done this is we would have had every record would have had 21 characters long set aside for the party field there. Instead of values stored for each field being 21 characters long, each field is now just 3 bits long. The full text for each entry is stored one time. So look at it this way. And the math is not super hard because we've got a pretty small table here. But if we said that Democratic Republican was 21 characters, so we had to account for a field width of a maximum of 21 characters. And there are 44 records. So 21 characters times 44 fields is 924 characters. And if we use a traditional, we're not going to look at Unicode or things like that, that would mean 924 bytes to store that vector of different parties. But if we move to this new structure, now make sure you understand the math here. It's not that hard, but it's important. I have a dictionary. The dictionary has to have 21 characters because the dictionary has to account for Democratic Republican. But you could think of it, this guy over here is basically its own database table. Okay? The dictionary is its own table, and the dictionary is 21 characters times only 6 fields, so that's 126 bytes. And then when I go back to my attribute vector, the column is 3 bits times 44 fields, which is only 16 and a half bytes. So I took what before was 924 bytes and turned it into 143 bytes just by doing what's called dictionary encoding. Well, suppose I take my whole table and dictionary encode it. Here's what we would have. We would have a last name dictionary, we would have a first name dictionary, we would have a state dictionary, and we would have a party dictionary. Now what's interesting about this is, when you look at this, remember there were, what did we say, 44 presidents? Well, 44 presidents have 37 unique names. That's because we've had multiple presidents with the last name Bush. We've had multiple presidents with the last name Roosevelt. There's some repeats there. First name, this is kind of interesting, 33. You know, we've had, I think, multiple Georges and Richards and such. But then state, we only have 16 states. So if we do the math on this, and what we see is here in the blue, and I'll make this a little bit bigger and we'll look at this. So here in the blue, the last name, if we looked at the data, we might have said, all right, for last name, we're going to allocate 40 bytes because some presidents have really long last names. So 40 bytes times 44 fields, that meant that would take up 1,760 bytes. First name, we'll allocate 40 bytes to that as well. You know, this is one of those database design decisions. 44 fields, 1,760 bytes. State, 20 bytes. Now you might say, couldn't we get by with just the 2-letter abbreviation? We could, but in this example I stored the full state name. 20 bytes times 44, 880 bytes. Party, 21 bytes times 44, 924 bytes, which means the old style way of storing this would have taken 5,243 bytes. But instead, we're going to do the dictionary encoding. Now notice what happens here, because some of this we get a different scenario. With the last name, there were 38 unique last names. So what we would actually have is in the dictionary, we would have 38 unique last names times the 40 bytes. But then we would also have just the column the attribute vector. So the 38 times 40 gives us the 1,520 bytes that's in the dictionary, but then this guy over here on the left, that's just the numbers that go with it, that's 33 bytes. So when you do the math on that, we save 207 bytes, which isn't that much, but we did save some things. And so you can see that some fields, depending upon how much repetition of value there is, the savings here can be pretty substantial. Well, if we look at a more realistic table that looks something like this. Okay, this is a fun little table I made up that, well, let's just look at it. We have last name, we first name, state, party, likes dogs. Okay, and in my rather silly example here, when he was a little kid, Zachary Taylor got bitten by a dog. And Benjamin Harrison had his dog die when he was really young. And so it scarred him for life. Neither of those two like dogs. Everybody else, though, likes dogs. Well, think about what your attribute vector here would look like. How many possible values are there for likes dogs? 2. There's Y or N. How many bits do you need to store that? 1 bit, right? You could use 0 for no and 1 for yes. You could encode every one of those presidents in 44 bits. Tiny as compared to even storing just the full letter Y or N. Then you get weird things like likes jelly beans. And you probably don't remember this, but it was well known that President Reagan really liked jelly beans. So he gets a Y, and we quite frankly don't know if George Washington, I don't even know if jelly beans existed way back then. So we have a field here that some fields have values, some fields don't. And then we get weird things like, well, not weird, but, gender. Not a lot of diversity of choices up there because, at least to date, we haven't had a female president. So every one of those values is exactly the same. Well, think about what we were talking about now, not only with this idea of doing a dictionary, but think about ways that we could also make this more efficient if we started thinking about things like compression techniques. And once again, you might think, well, what's the big deal here? Well, if I am writing this data from left to right, and remember my example of using the Ditto mark, how many times do you ever see the same data show up back to back to back when you scan from left to right? Would you agree with me that almost never happens? I have this fun little picture, which is kind of silly, but I'll show it to you anyhow. Until we elect a president named Virginia from Virginia, you're probably never going to see the same first name, last name, and state in a row, right? I mean, that's not the way the data works when you look at it based on looking at it as a record. But when we turn it 90 degrees and we start looking at it as an attribute vector, we see a whole cluster of reds show up one right after the other. We see these clusters of Republican show up. We see all kinds of things like that when we look at from a data profiling perspective, now all of a sudden we can think about ways of really making this much more efficient in terms of storage. Let me give you an example. Compression. We will talk about one very simple method of compression. It's called run length encoding. Okay? Now, here's what I did. Here's the party attribute vector over here that we saw before. Let me make this a little bit bigger. And this is now going to rely on just the whole idea. A lot of what compression is people look at data and they think, how could I represent that same data in a smaller amount of space? And run length encoding simply does this. Run length encoding, you look at a value and you ask yourself, how many times does that occur? And you write that down. So run length encoding says, all right, the first party is 3 and it occurs 1 time. The next party is 2 and it occurs one time. The next party is 1, and it occurs 4 times. And so we traverse the attribute vector doing run length encoding, and we get a much smaller footprint of the data. SAP looked at all of this, and in their research group, they did some very interesting things that I want to show you, and then we will see what questions you guys have and talk about that. What SAP did, and they actually created this. I give them credit for this because this would have been just kind of a big headache. They created a table that simulated a table that contained basic information from everyone in the world. Okay? So we have a database table for all 8 billion people in the world. And here's what they did. They created a traditional row store database. So first name, a lot of people have really long first names. So we're going to allow a first name to be 50 letters long. Design decision. You might say, well, couldn't we get away with 45? Sure, it doesn't change the numbers all that much. They said 50, and there are 8 billion people. So 8 billion times 50, that's 373 gigabytes. Then we're going to do their last name. And we're going to do 50 letters for their last name. 50 bytes, 8 billion people, it's another 373 gigabytes. Gender. We only need 1 byte for gender, okay? Now, that's something that might change in database design in the future, but right now, traditionally, you allocate 1 byte for gender. 8 billion people, that's 7 gigabytes. City. Some cities have really long names, 50 bytes for city, so we got another 373 gigabytes. Country, I don't know why. I guess just to make the math look a little bit different, they decided that countries are only going to have 47 letters in it, so that's 350 gigabytes. And then birthday. You can store someone's birthday in just 2 bytes, and I think that's not storing even. You might be able to squeeze their full birthday in there. That might not have the year. That might just actually be the year of their birth. I'm not sure. 8 billion, 2 bytes, 15 gigabytes. That database table was about 1.5 terabytes. So what if they went back now and they said, suppose we use this technique that we just talked about here. Although there were 8 billion people, not all 8 billion people have unique first names. There are a lot of Bobs and Sues and Joes. So in fact, there were only 5 million unique first names. So you create a dictionary that stores all 5 million of those names just one time, and then you create an attribute vector that matches that. So what you wind up with is a dictionary that's going to be 21.4 gigabytes because you're writing each name just one time, and then your attribute vector is going to be 0.233 gigabytes, which means you went from before this being 373 gigabytes to this being in the neighborhood of 22 gigabytes, you just saved 351 gigabytes. And by the time all of this was done, notice this, with birthday, no savings at all, because you just have a lot of unique birthdays out there. I mean, basically, if you think about it, you've got to account for every day in the calendar, because there were people born today and there were people born 100 years ago, and there's probably somebody on this planet that was born every one of those days. So you don't really pick anything up in the way of savings for what you're doing with the birthday, but what you have is, and this is where this gets so amazing, old school row store about 1.5 terabytes. New school column store 86 gigabytes. That's a huge differential. Now, could this possibly work in the real world? So, what did SAP do? SAP went to their customers. They went to several of their big customers that they partnered with a lot. SAP does not talk about who they field test things with. But from hints they've dropped, I think one of the companies they worked with was Procter and Gamble. Went to that company and said, "We're developing this new product. We've got this new idea for a database. Will you let us take your enterprise database and see what we can do?" Well, how much could they shrink it down? They took a real world database and made it 1/17 the size just by dictionary encoding it. And notice with this table right here, we're not doing any kind of fancy compression or anything else. This is just straight dictionary encoding. So we can take a database and we can make it a lot smaller. Now that raises a question, who cares? Okay, you made it smaller. Well, when you make it smaller, now you can do some really interesting stuff. 1.5 terabytes is like going to have to go on a hard drive or some pretty large scale storage device. 86 gigabytes is something that you could probably put on cell phones these days. When you can get this data much smaller, you can now put it places you couldn't put it before. And what's really cool about it too is it now is a lot less data to move around, so you can actually manipulate it faster because it's smaller too. Well, let's look at how this actually plays out. Okay, here is a picture, and here is the old school row store database is what's being depicted here. And suppose we ask the question, how many men and women are there in the world? And your answer, you decided to answer the question by doing a select star on gender and counting how many values showed up, okay? Let's assume you're really bad at writing queries, because that would be a horrible way to do it. But that's what you decided to do. Well, what actually happened when you wrote a select star is the computer went out and fetched everything. Even though really to answer your question, all you needed to do was to look at the gender field, but you fetched a whole lot of data that you never used, which is one reason why hopefully in your database classes you've taken, it was beaten over your head to not fetch data that you ultimately don't need, and to be really, really careful about select star operations, because they're almost always overkill. Well, let's assume you can see in this you fetched a lot of data that you didn't actually need. Well, now we're going to do this. Suppose you got better at your writing of query and you wrote a select gender query against a row store database, okay? So now we're not going to fetch too much data. But there's something about databases that most people fail to account for. And this is something that you might have talked about in an architecture class or something like that. This is a concept called stride access. And it has to do with how computers actually go out and grab a hold of information. When you tell it, well, let me start with this. Let me give you my analogy for stride access. Here on the right side of the screen is a bucket. Okay? Here's my story. You decide later this afternoon to go out and you're going to take a walk by a lake. And as you're walking by the lake, you decide that you see a fish swimming by, and you want that fish. Maybe you're going to you want to look at it more closely. Maybe you're going to catch it and cook it for dinner, but you see a fish, you want to grab the fish. Well, so you reach in with your hand and try and grab that fish. And unless you're really, really talented, probably the fish is going to get away from you, because it's hard to grab a fish with your hand. But you look, and magically enough, sitting on the ground next to you, there's a bucket. And you grab that bucket and you stick it in the lake, and you can fetch the fish with the bucket. Now, when you pull the bucket out of the lake, do you get the fish? Yes. But what do you also get in that bucket as a byproduct of getting the fish? You get all the water that was around the fish, right? So you might then, now that you have it in the bucket, you grab the fish, and then you dump the water back into the lake. Well, that same concept represents what happens when a computer goes out to storage to grab data. Depending upon the size of the machine and its architecture, when it goes out, it may grab 16 bits, 32 bits, 64 bits of data in its bucket, because that's the size of data it retrieves. That's called stride access, and architectures have different stride access. So look at my picture now and think about the bucket. You stick your bucket in, or the computer goes out to read the gender in the first record, and it gets the gender, which is what it was looking for, but it also gets the data that's around gender, just because that's the smallest amount of data it can grab at one time. So it winds up grabbing the country field too, even though you didn't ask for it in the first place. Then it goes to the second record and it sticks its bucket in and pulls this back, and then it does this and pulls this back, and then at the end of the process, it's going to throw away a lot of data that it retrieved because of the way this actually works in the data handling architecture. Well, suppose we're looking at a column store architecture. All the first names are stored together. All the last names are stored together. All the genders are stored together, and so on. So sticking with my example, if you stick your bucket into the gender pool and pull it back out, everything in your bucket's a gender, right? And the last time you put the bucket in, you might get a little bit of country. But until that very last read, everything you got back was nothing but gender. So not only by turning it this direction were we able to employ dictionary encoding and perhaps do some encryption, but now the process of going out and fetching it has actually become much more efficient. Now, that raises a very obvious question, which is, suppose you need to reconstruct an entire record. Well, remember, in row store, all of the attributes are stored consecutively. So here's an example. Suppose a record is 200 bytes in length, and you are working with a machine that has a stride access of 64 bytes. You're going to have to stick your bucket in 4 times to retrieve that one record, and you're going to get a little bit of the next record on that 4th read. Well, if you're working on a machine with 2 megabit access per millisecond per core, that's 0.128 microseconds. That's a millionth of a second with a single core processor. If we have to do the same thing on a column store database, well, now we're going to have to stick the bucket in first name, stick the bucket in last name, stick the bucket in gender. We're going to have to do one read from each attribute vector, which in this case now means 6 cache accesses, which means this just got slower. But there's something that changes this in the real world that could really make this interesting. It's this guy right here. See, if we go back here, if I am fetching data that is stored contiguously like this, I'm going to go after this with a single microprocessor core. If I'm going at 6 independent attribute vectors, if I have a multi-core processor, That's essentially like saying each core has its own bucket, which means those 6 different fetches could happen simultaneously, each in a different core, and then they could be aggregated after they've been fetched. So this is now where, if I have a table that has 54 fields, and I have a processor that has more than 54 cores, in one fetch operation, I can actually reconstitute a record. So, Microsoft, SAP being SAP, they did some very interesting tests. Remember, they created this database table, so they were going to do a lot of things with it. They said, okay, suppose we hit this database table of 8 million people. They put it on a very, very fast server, and they said, let's do a select star. How long is it going to take the processor to do a select star? And the answer is 800 seconds. So that's what? That's over 10 minutes to do a select star operation on 8 billion records. When they changed it on a row store to select gender, performance time dropped to 256 seconds, but that's still over 4 minutes. When they did select gender on a column store database, half a second. Now, you might say, these are all really kind of interesting, fun numbers. Can you really, really, really make things fast, this fast? And SAP's answer to that is, and I don't know to what degree this is the way it really played out, but SAP said, we got this idea by looking at Google, for example. You go to the Google search engine and you type in a string of words and you hit the enter key, and in less than a second Google fetches your answer. How in the world could they possibly do that? I mean, they're querying databases and they're coming back with answers to queries. What I like to do is go to Google and try and type a sequence of words in that like nobody has ever typed before. Like peanut butter, elephant, daisy, and just string together 15 random words, hit the enter key, and still Google gives me an answer in less than a second. Okay? How are they doing this? Well, all that's happened is SAP and SAP's competitors are stealing techniques that Google and other companies like that have been using for a long time to create search engine results. And the point of all this is, if we can take a query that used to run in minutes and get it to run in sub-second time, the world of enterprise information systems changes dramatically. One of the companies that I've done some consulting work with recently moved to an SAP HANA system. And they had a traditional data warehouse, and there were a lot of queries that they would run overnight to build different reports, because the queries would take 10, 15, 20 minutes to run, some of them in excess of a half an hour. At one of the training sessions, and I wrote this down, and I want to see if I can find it here. Here it is. One of the gentlemen said that there was a particular query that they had that went against 250 million records in their transactional database, and it took 20 minutes to run. They loaded it up in HANA. They told HANA, and you can tell it automatically, make it a column store database, and HANA takes care of the conversion. HANA will also encrypt the data and compress it. You don't know what compression algorithm it employs because it's going to profile the data and pick. And they did go through and optimize their query a little bit. Runtime, 1.5 seconds. From 20 minutes to 1.5 seconds. This is where people get really excited, because now we can start thinking about putting this places that we never could do it before. What you're seeing there on the screen is some screenshots of an application that SAP has out called SAP Fiore. SAP Fiore is an interesting architecture. We might have talked about it earlier, where you have all of these tiles, they call them, that users can load up on their desktop, and you essentially can go to like a company app store, and you can, depending upon your role in that organization, you can put different tiles on your desktop, and all you can see, the tile typically has some basic information on the tile, maybe some kind of display about company performance, and then you can click on that tile and get more information. What this is enabling companies to do now, and it's here in the title, is before, ERP systems were about giving people transactional information. Think about playing ERP Sim and how you can look at a sales report and you can see your sales information, but it's really hard to draw meaning out of that because it's just presented to you in a table format. Well, now, if we can handle more information more quickly, we can put the analytic display right next to the transactional data so that someone can pull up their iPad and instead of seeing tables of information, they can see pictures. And the thing about Fiore that SAP touts is, you create, and if you look here, the same thing showing on this desktop is also showing on the person's iPad, and then when they look at it on their iPhone, you don't see as much at the same time, but the same tiles are there on your iPhone as well. And so now you can move back and forth between environment, and because the performance is fast enough, you can actually do very interesting things like create an app that you could put in the hands of your salespeople where they could pull up a map of the United States. I actually saw a demo of this system. SAP did it at Sapphire a few years ago, where you can pull up a map and it'll show all your customers on the map, and you can touch their dot on the map and it loads up like the address of the company, a map that shows you where they are, and all the things they've bought recently from your company. And you could even look at things like promotions that they were sent and other things of that sort. This is now something that, because you can run a query in less than a second against full enterprise worth of data, becomes really, really, really interesting.
Why did it say near future?
In this right here, this is because, what this is, and I don't know that we've talked about the history of this, but the very first product that SAP brought to market was called System R, where R stood for real time. And then they came out with R2, and when they came out with R2, they went back and renamed this R1. And then there was R3. And actually, the software that a lot of companies are running right now is a variation on SAP R3. Well, when SAP moved to this new HANA structure, they began to realize that they could change the whole underlying data model, and instead of needing thousands and thousands of tables, they could create now column store database tables that's one table that has 1,500 fields in it. And you can now do away with a lot of joins and other operations like that. You can just store the data materialized and already joined. So they went back in and they re-engineered their data model, and they said, we need a different word for this. So they brought out a product called S4, where the 4 is just the increment here from where they were using numbers before, and instead of R being real time, the S stood for simple. Because the idea was the underlying data model was going to be much simpler. Well, the reason why I put the near future is because SAP basically had this great idea, and they said, what this means is we're going to have to rewrite our product from the ground up. And what is the number? I want to say that SAP ERP is 150 million lines of code. I heard a number. I want to say it's in that neighborhood. It's just outrageously huge product. You can't say, okay, team, rewrite that by next month. Doesn't work that way. So what SAP did is they said, we're going to come out with this S4 product, and we're going to release it over time, module by module. And they started with simple logistics. And then they went to simple finance. And then they went to simple planning. And they haven't yet released the full suite of everything. They're still working on it. But over the next few years, eventually, the entire SAP infrastructure, customers will have to run HANA because they won't have an option. And all of these old things are going to go away in lieu of this, what they're now calling their S4 architecture. But it's not fully there yet. It's being rewritten, kind of as we speak here.
Lost me a little bit when you said all one database or one table is. Can you include a dictionary? Talking about excluding a dictionary?
No, the dictionary you would still have the dictionary. The idea would be like right now, if you wanted to know information about materials or accounting documents in an SAP system, a very basic, you want to know the basic facts of a material might be spread out over a dozen different tables. Just a simple accounting document is spread out over dozens of tables because of the data model. And SAP, the idea here is now that we can create database tables that are much wider than what we used to do, because we now have this whole new way of thinking about the way the data is going to be stored with a column store, we can make these tables there. Everything about a material is stored in one table. So we no longer have to have all of these different tables. So it's simpler in that you're going to have fewer tables and all of the information about a thing is going to be stored together, which immediately brings to mind the fact that a lot of things you talk about in a database class regarding data normalization and all of that is going to change. But what's important to realize is in a HANA database, and we haven't talked about this, this is a good transition, sometimes you want to stick with row store databases, tables. It's not like everything should be column store. So what you have is a database that can have column store data and row store data. And there's a lot of data, like a log file, for example, where you're just recording things as they occur and it's based on time. There's no reason to separate that into different attribute vectors in a column store table, because when you process it, you're going to be writing an entire record and you're probably going to be retrieving an entire record. So we still have row store databases. Table.
Store, ACID compliant.
Yes. Oh, absolutely. Absolutely. You're not going to lose any of that. Now, what we have gone through, and we're not done yet, are the fundamentals of this. If you really want to dig into this a little bit more, what I really recommend is there's a one of those massive online course systems that's free called Open SAP that has a lot of different courses in it. But beyond that, there's Hasso-Plattner Institute, which is based at Stanford University. And there's actually a free class that you can take through OpenHPI. You just do a Google search for OpenHPI, you'll find it. There's a class taught by Hasso-Plattner on in-memory databases that's like 30 hours long because it's an entire college class. And he goes into this in great detail. Really, really great course. Lots more of the nitty-gritty details than we have talked about here, but a really good way to learn more about this. Oh, here's what I was saying. We're talking about S4, the 4 promises that SAP has made with 4 is everything. Native in memory, which means that since we now know we're going to put the database in memory, we're going to rewrite the whole system to take advantage of that, which means that that's going to have a fundamental change in the way we write queries, the way we paint screens, the way transactions work. Native in memory, and exactly what we were talking about a moment ago, simple, and I think we have to put that in quotes, simple data model, improved user experience. They want to get rid of the SAP GUI. What I was showing you a few moments ago with Fiore, that may continue to evolve. I'm sure it will. But the idea of the SAP GUI like you guys have been using, its days are numbered. They're trying to get rid of that. And then the last thing, I include it here because it's one of their 4 promises, guided configuration, which essentially means SAP is saying it will be a lot easier for companies to set up a system, and it will be the kind of thing that the system will help you more with than historically has been the case. Basically trying to make it easier for companies to implement. But what this does ultimately is, here's a slide from Hasso-Plattner Institute, and this goes back to kind of where we started. If you go out and you want to read something off a really fast hard drive, a typical disk seek is going to be 10 million nanoseconds. Well, if you can see here how much faster a solid state drive is. I mean, a solid state drive, a lot of you have that in your laptops and such, much, much, much faster. But notice this, main memory, 100 nanoseconds. And if you can actually read it from L1 cache, half a nanosecond. So, I mean, when you're talking about a difference between 10 million nanoseconds and 100 nanoseconds, that's not like saying it's a little bit faster. It's so much faster to not even be comparable. And that's why this is now kind of a whole new world. The vision, and I've seen prototypes of this, is the vision is that someday a manager might be able to sit down at a computer and have a Google-like interface where he or she could type in, show me sales of a product in the South, and just describe something, and the system brings it up and presents it. We're not there yet, but that will be there.
Voice activated as well.
He was at, Dr. Berg is at Lenore Rhine,
Yes.
and he was going to come and speak this semester, but he's had to push that back till next semester. Go to his presentation if you can, because he's going to talk about, some of the examples of this that companies are playing around with. It is where Google, Google, the speed, things like Apple and the idea of an app, we're now dragging that into the enterprise information system space. And it's because of things like this. I pulled this picture out right here. This is a system made by Lenovo. This is the Lenovo 3850X6. You could put this on your Christmas list for Santa, I guess. 72 cores, 6 terabytes of RAM, backed by 12 terabytes of flash storage. Costs $15,000. Now, $15,000 is not free, but when you're talking about buying a server for a company, that's not really that outrageous. Lenovo is expecting to bring a CPU to market this year, one chip, 4,096 processor cores on it. I mean, that's where the industry is heading, because now all of a sudden companies have a use for this. And so this is more of what you see. The interesting thing about this is if you really wanted this device and you called up Lenovo and said, here, let me give you my credit card number, they probably would tell you that they can deliver that to you in 6 months. Because the problem right now is there's such demand for these devices, and there's a shortage of the componentry that goes in it. And so now a lot of companies, I know a couple of companies I've talked with recently, they're going with cloud providers, not because really they're that enamored of the cloud, but the cloud providers have the hardware, and for them to buy it themselves is going to take 6 months to a year.
Yeah, I think last time I looked at it, SAP charged per core licenses. Is that right?
SAP has so many different ways of charging companies for stuff. But it's a negotiation, and whenever you start talking prices with SAP, the conversation always turns to, well, we'll have somebody sit down and talk with you. But yeah, they'll license it to companies, sometimes based on number of users, sometimes based on the processors
I was wondering more in
itself.
technical terms, not so much in the business terms, but if money was an issue, you have, say, a 16-core server, it would be the most efficient to put a SAP license on each core.
You can, and I haven't priced it in a while, but you can go out to AWS, and they have HANA systems in the cloud where you can specify how many cores you want, and the prices are actually not that outrageous for companies. And some of it is where you bring your own license, so you have to negotiate that part of it with SAP. But you also have SAP runs its own cloud, and they'll run the HANA systems, and you can just do it in a multi-tenant type architecture. So all of this, the reason why a few slides ago I said, the near future, because a lot of this is, we don't have this fully formed right now, but we have several graduates of ETSU that are working in companies in this area that are developing Fiore apps. And companies like to hire new, younger people to do a lot of that, because in some instances, the people that they have are more veteran, are very expert in a particular set of things, and they don't want to pull them off of that. And so they hire new people and throw them at new projects. And in some cases, the people that are experts at this don't want to learn anything else. So companies hire new people because they figure, they don't have that bias and they can throw new projects at them. So, some of you in the near future, might have opportunity to work on a lot of this technology for companies, because it is something that they are very, very interested in. When this technology first came out, it was super expensive. And in this area, the only company that had moved to this technology was Eastman Chemical. Well, prices have come down to the point, as an example, that the University of Tennessee is now running HANA. University of Tennessee, like ETSU, isn't exactly a wash in money, but it was affordable for them. So the price for this stuff has really come down. And so whereas it used to just be Eastman Chemical, now in this region you have Eastman, you have Oak Ridge National Laboratories, you have Y12, you have a lot of companies that are running this technology and hiring people to work with it. So, questions about any of the things that we have been talking about here? There's a lot of stuff I didn't cover, so if you have questions, please ask them. But I do think, as far as kind of the core ideas, hopefully this made sense for you. And let me do this. Let's go back to what we started with, which was this slide right here, where we talked about, row versus column. We talked about dictionary encoding. We talked about the idea of an attribute vector, and we talked about compression. And then all of that lets us put this in memory, and it gives us the kind of results we're talking about. Mm-hmm. Yes, sir.
And my question is, SAP, this is proprietary to SAP.
HANA is, yes, but there are other companies that have their variation on it.
Concept of in-memory database and everything we spoke about is all
Yes.
So, for example, Oracle is proprietary to Oracle and it's enterprise database, but there are things like MySQL and Postgres that can give us same kind of resources when we use them as personal. Is there anything like that that can do this kind of column-related in-memory thing in the open source world that people like us can play with, or you have a small company that can afford enterprise-related applications?
You know, I have not studied to see if, for example, if MySQL is doing anything in this domain. I don't know. Yeah, I think that your point is a very good one, which is conceptually, as far as the things that we've talked about, pretty much everybody's product works the same. Where the difference is what their compression algorithms look like, and then in the actual database when you're talking about the functions that are available and the things that it will let you do, how they optimize around that will be very different. For example, SAP has they call it PAL, which is their predictive analytics library, which is a whole set of functions that you can use on data to do various statistical analysis, and you can basically do that right in a query. Well, that's the part of it that's unique to SAP. So I'm going to guess that eventually the open source community will have something like this. Heard of what? CouchDB? I'm not familiar with
It's
that.
a little bit different though, right? That's like the NoSQL.
Yeah, and you do have things like Hadoop, for example, that will give you, some of the pieces of this. But the whole idea behind this, as far as the big performance focus, I don't think you're going to see an open source product deliver that level of performance.
Another thing is, from what you explained about compressing a lot of tables into one, this basically changes the way we write applications. Because ideally, if I was an application, I'll take an application, I'll design a relational data model with data, all that stuff. But now, it seems as if the database takes care of turning my work into a normalized application. So the way I write an application for SAP HANA, considering that it's going to do all of this, will be strictly different from the way I write an application for a normal MySQL database. Right? And that's what I wanted to ask if that.
What you're going to see, and keep in mind a lot of this is still evolving, but what companies are realizing now is that to really get the performance at the highest level they can, it's kind of like, I've used the analogy of race cars before. You can buy the same engine, but some people are better at tweaking it and tuning it than others. What companies are beginning to see now is that the skill in which someone writes a query is becoming a lot more important. And so ironically, a lot of companies now, they're going back in, and first of all, they're getting rid of all of the select stars because those are horrible. But then beyond that, they're looking at ways, how can we take this query and how can we really, really optimize it using stored procedures and using things that are part of the particular database infrastructure we're running to get this down, because there's a big difference in a query running in, let's say, 6 seconds and a half a second. Because 6 seconds when you're tying it to a mobile app is kind of painfully slow, but a half second is almost instantaneous. So to get the best performance, the focus now is going to really, really shift to the importance of writing the query. The interface is the interface. It's the fetching of the data and that manipulation and optimizing it where a lot of the focus is now. So I think it would be fair to say in the realm of database, there probably is going to be less emphasis on the database design because that's largely been done for you by the vendor, and a lot more focus on being able to interact with and manipulate the data in the most efficient and effective way in the query. And I'm telling you, companies right now, they're looking for people that are really, really good at database stuff, because that's what you need to really take advantage of this. Other questions or comments? The attribute vector is just the term that we use for when we take our let's find what would be the best picture. This right here, this that I've color coded, this party here. This is an attribute vector. You think about, what is it in geometry? A vector is just like a straight line. This is an attribute, in this case party, and it's just a straight set of that data. So we just use the term attribute vector.
I want to say something about at the beginning you listed three other competitors or so. IBM, Sybase, Oracle, Exadata, and all that.
Mm-hmm.
I wanted to say about Exadata, and from my research, I worked with it, and it's actually the machine itself. And any kind of Oracle can put into it. Oracle 11G is not an in-memory database, but the new Oracle 12C actually is an in-memory database, like a Computational HANA, that can be installed into a machine called Oracle Exadata machine.
It is kind of interesting, and I'm glad you brought this up. A lot of these companies that used to kind of think of themselves as a software company, like Oracle, for example. Now a lot of them really want you to buy their hardware too, and they're really, really speccing out the hardware and then tying their architecture on the data side to the architecture. And it goes back to like a lot of things we talked about with Stride Access. If you can really control the architecture and you can optimize around that, that's how you're going to get that last little bit. That's why you go to a Google data center and all their machines are their proprietary hardware. The way they built it, they're not just kind of using generic PCs to give them the performance they need.
Another popular database you mentioned, CouchDB key value pair. That's different than HANA, right? Is HANA still considered relational?
It is.
It's just
Yeah, it's all, you can write the same old queries. You could write the same old bad query and it runs the same. And that's why a lot of people think that the world just changes dramatically. A lot of this is your world doesn't. When you get under the hood, things work very differently. But you're still writing the same kinds of query. The key is understanding more why you don't want to write certain kinds of queries and how you can perhaps optimize your query based on your knowledge of how the data is represented. But yeah, everything is, SAP always has to make everything fully backwards compatible. So everything is, the query is still going to give you the same results that look the same way. Other questions? All right, well, I won't see you next Thursday because of Thanksgiving. I hope everyone has a good holiday, and we will assemble the week after that. Have a good rest of the day. I did record last week's session, but I didn't get a chance to upload it to YouTube, so when I upload this week's session, I'll also put last week's session up as well. Have a great afternoon, everyone.
Will this be on D2L?
Yeah, I will put this up in D2L before the week is up.
My presentation for research methods, I'm